Good morning, children. This is class 12th, unit number 3, magnetic effects of current and magnetism, chapter 5, magnetism and matter. So, let's start with magnet. So, children, around 2000 years ago, on an island of Greece, the island's name was Magnesia. A material was found, and children, this material, it had a property to attract iron, cobalt, nickel and steel towards itself. Now children, as this material was discovered on the island, that is Magnesia, it was named as magnetite. The material was named as magnetite, which today we know as magnet. Okay, so the chemical formula of magnet is Fe3O4. So, natural magnet is an oxide of iron. Now, a property of magnet, let's discuss a property of magnet, that is if you freely suspend a magnet. Freely suspending a magnet is, that is you are tying a magnet with a thread and then you are hanging it on a stand. So what will happen? The magnet will move for some time and after that it is going to align itself. It is going to set itself in a particular direction. So the freely suspended magnet, it aligns itself in the north-south direction of the earth. वो अर्थ की नॉर्थ साउथ डायरेक्शन में खुद को सेट करता है, खुद को अलाइन करता है. This property of magnet is known as directional property, or it is also known as directive property of magnet. And this directive property of magnet is used in magnetic compass needle in order to find the direction. So, the magnets which are occurring naturally in the nature, they are just like stones, means they are of irregular shape and their strength is weak. Right? This is about natural magnets. Now, such weak strength magnets cannot be applied cannot be used in many applications. So what did man do? He made magnet, right? What he is doing? He took an iron piece and he is rubbing it with a natural magnet, or he is placing the iron piece near a magnet and leaving it there for a long time. What was observed? It was observed that after some time, the iron piece, it becomes a magnet. It acquires the magnetic properties. It also starts attracting small pieces of iron, steel, right? So it also behaves like a magnet. Now this iron piece, which we have made it into magnet artificially, so such magnets are called artificial magnets. Right, children? Now, these artificial magnets, they are made in different shapes according to our convenience and according to our requirement. So, the generally available artificial magnets are bar magnet, horseshoe magnet, or in the shape of a needle, that is the magnetic needle. Now children, let's talk about bar magnet. So bar magnet, children, they are the simplest form of artificial magnet. They are the simplest form of artificial magnet. Now, the strength of the magnet at the poles, at the edges is maximum. North Pole and South Pole. At the edge, the magnetic strength, power to attract is maximum. So this can be verified. This can be verified with the help of experiment. So what are we going to do? We are going to sprinkle. Sprinkling is what? Chidkav karna, right? So we are going to sprinkle some iron powder on a cardboard, right? So you take a cardboard, on the iron cardboard, you just sprinkle some iron powder. Then you are going to place a bar magnet just below the cardboard. Just below the cardboard, you just keep a bar magnet. And you will observe that the iron powder, the iron fillings, it arrange itself in the pattern shown to you in the diagram. So if you study this pattern carefully, you will see that the maximum iron powder gets accumulated at the edges of the pole, at the pole. Maximum iron fillings is attracted or they get accumulated at the pole, showing that, proving that the magnetic attraction at the pole is maximum, proving that the magnetic strength is maximum at the poles of the bar magnet, right? Chalo. Now next move to the next slide. So now let us discuss some of the basic properties of bar magnet. Now, every magnet attracts small pieces of magnetic substance like iron, cobalt, nickel, steel, right? And bar magnet, just now we saw that the force of attraction is maximum at the ends of the pole and at the ends of the magnet, and these ends are called pole, right? This is the property which we just verified it. Second property also we have talked about, that is if when you freely suspend a bar magnet, then it will align itself, it will set itself along the north-south direction of the earth, along the north-south direction of the earth, along the geographic north-south direction. Now, let's proceed towards the third property of a magnet. Now, this is your bar magnet. Now, if we draw a line, a straight line passing through the center of the magnet joining the North Pole and the South Pole. So that line is known as the axial line, right? The line joining the North Pole and the South Pole of a bar magnet is your axial line. And the line drawn perpendicular, or the line drawn through the center of the magnet, a perpendicular line drawn through the center of the magnet is called the equatorial line. So children, the angle between the equatorial line and the axial line is 90 degree. So equatorial line and axial line are mutually perpendicular for any bar magnet. Fourth property, we are very well known with this, we are very well familiar with this, that is the like poles of the magnet, they repel each other, and the unlike poles of a bar magnet, they attract each other. Let's talk about the inductive property. So inductive property says that if you place a piece of soft iron, cobalt or nickel near a bar magnet and you leave it there for some time, then when you return and see the soft iron piece, the cobalt piece or the nickel piece which you have kept very near to the bar magnet, it is not touching, children. You have kept it very near to it, very near to the bar magnet. You will see that that piece of soft iron, that piece of cobalt or nickel has acquired the properties of magnet. It has become a magnet. So this property is called the inductive property. That is the property of magnet of magnetizing soft iron, cobalt and nickel by placing it very near to a bar magnet without touching it is called inductive property. Now the last property which we are going to study is the bar magnets. They always exist in pair. That is, as you can see here, this is a magnet, north pole and south pole. Suppose we break the bar magnet from the middle. So it will not happen that one side you will get north pole alone and the other side would be south. No. The broken pieces, in the broken pieces you will have, each piece will have a north pole and the south pole in it, right? So this proves that the magnetic monopole means single pole, alone north or alone south can never exist. Now, in order to show the magnetic field, the scientists, they showed it graphically with some lines, right? So we will be talking about that lines also, but before that, let's talk about magnetic field. So children, we have already done in class 10 magnetic field. So magnetic field, as you used to play in the school ground, in the school field, right? So what is that field? Field is an space, it is an area, right? It is a region, and that region is around a magnet or it is around a wire which is carrying current. Around that region, a space. In that region, the magnetic force of attraction or repulsion is felt if you bring another magnet in this field. If the magnet is here, no force, magnetic force will be felt by this magnet. But once you bring the magnet within the space, in the space, then the force between the two magnets, or if you bring here another current carrying wire, then the force between the two current carrying conductors will be felt, right? The force, the magnetic force will be felt. So that area, that region around a magnet in which the magnetic force will be felt by another magnet. So that region, that space is called the magnetic field. So magnetic field, right? Now, so another concept was given by Faraday, that is to view, that is graphically to see the magnetic field. He gave the concept of magnetic field lines. So this also we have done in class 10th. Magnetic field lines are what? They are not real lines. They are imaginary lines, right? They are imaginary lines. They are such lines that if at any point, suppose I want to find, we know that magnetic field, it is a vector quantity, magnitude and direction. Suppose at point P, I want to find the direction, that in which direction the magnetic field would be. Then what I need to do? I just need to draw a tangent, right? What is a tangent? A tangent is a perpendicular line, perpendicular to the radius of the circle. Suppose I complete this, here something we are going to have a radius. So tangent is your this black color. Let me make it of black color. This black color tangent is making an angle of 90 with the radius, right children? And it touches the circle at only that point. So that tangent, it shows you the direction of magnetic field. So that is your magnetic field lines. So magnetic field lines are what? They are imaginary lines. First thing, they are not real, they are imaginary lines. They are imaginary curves. Such that at any point you draw a tangent, it gives the direction of the magnetic field at that point. Right? So that is your magnetic field lines. Now, there are two types of magnetic field, as we know. If you are having uniform magnetic field means in that region, in that area, the magnetic field strength is same. Magnetic field strength is same at all the places. So if you want to represent that magnetic field, then you are going to draw straight parallel lines equidistant from each other. The distance between them should be equal. They should be drawn with scale straight parallel lines. So it shows that at any point, the magnetic field strength will be same as the other points in that field, right? So we have studied this, that magnetic field is sometimes represented by cross and sometimes it is represented by dot. What do they mean? See, cross means the direction of magnetic field is perpendicularly inside the paper, right? It is into the paper. And dot shows here that the direction of magnetic field is perpendicularly outwards. It is coming out of the paper, right? So this is your uniform magnetic field. Now let's talk about non-uniform magnetic field. Non-uniform magnetic field, beta, it means that the magnetic field strength, right, or its magnitude and direction of magnetic field changes with time. Magnetic field strength same nahi hai, direction bhi change hota ho raha, मतलब either magnitude is changing or direction is changing or maybe both are changing. So if you want to represent non-uniform magnetic field, then you have to represent it by unequal spacing, that is unequal spaced lines, or if the spacing is equal, here you can see the spacing is equal, means magnitude is same, but you can see, children, that their directions are different, right? So the area where the magnitude or where the field lines are very near. Here you can see that the space between the field lines, see, they won't be crossing each other. That we will study further, right? They are not going to cross each other. That is not possible. They are going to be very close. So in this area, if you see, the field lines are very, very near to each other. It means that the magnetic field over here is very strong. And here, if you see, children, the magnetic field lines are very far from each other. So as the magnetic field lines are far, it means that the magnetic field is weak, right? And in the second diagram here, you can see that the direction of magnetic field is changing continuously. Now let's talk about the properties of magnetic field lines. Now first property of magnetic field lines is that it always forms a closed loop. It always forms a closed loop. It is a closed continuous curve. We are done in 10th, right? And outside the magnet, the magnetic field lines will extend from north to south. Okay, so it is from north to south. North to south. But inside the magnetic field lines are from south to north, right, children? So outside the magnetic field lines are from north pole to south pole, and inside they are from south pole to north pole. These are the first two properties of magnetic field lines. Next, we have done this, that is, if the number of field lines that are passing through a unit area and that field lines are perpendicular to the area, you can see that this line and this line, right? This is x-axis and this is y-axis, so they are perpendicular. So if the field lines which are passing perpendicular through a particular area are more, means more field lines are passing through area that is perpendicular to it, Then if more field lines means the magnetic field is more. The magnitude of magnetic field is more, means strong magnetic field. But if in a if in a particular area, which is normal, which is at 90 degree to field lines, very less magnetic field lines are passing. बहुत कम, दो पास हो रही हैं. Then you will see कि मैम इसमें जो magnitude है ना magnetic field का, that is less, means the magnetic field over here is weak. Then the fourth point is very, very important, that magnetic field lines, they never intersect each other. Suppose if they intersect, as you can see here, the blue color, they have shown you the field lines and they are intersecting at point P. So children, for this curve, the tangent at point P is this, right? And for the second curve, the tangent at that point is in this direction. So at point P, two directions of magnetic field is not possible. Magnetic field, it will have only one direction, right? So we can conclude, we can prove that the magnetic field lines never intersect each other, because if they intersect, then at the point of intersection, two directions of magnetic field occur, which is not possible, right? So whenever you draw magnetic field lines, make sure your magnetic field lines never intersect each other. Next, the magnetic field lines, they exist even inside the magnet. As we saw in electric field lines, there you had a charge, right? The electric field lines, they originated from the charge, but inside the charge, inside the charge, the electric field lines were not present. The electric field was zero, right? But that is not the case with magnetic field lines. Magnetic field lines, they exist inside the magnet also. Okay, that is from North Pole to South Pole, right? Next, we saw here that the magnetic field lines, they are closed and continuous curve. But electric field lines, they were not closed, right? They were not continuous, right? They were continuous, but they were not closed. So this is the difference between the electric field lines and the magnetic field lines. Now let's proceed towards magnetic dipole moment. Magnetic dipole moment. Now children, every bar magnet, this is a bar magnet, every bar magnet, it consists of two poles, North Pole, South Pole. And these poles, they are having equal magnitude. Their magnitude is equal. Magnitude is equal, right? The magnetic field is, magnitude of magnetic field is equal, right? But they are only of opposite nature. One is north and other is south, right? And children, the North Pole and South Pole, they are separated by a very small distance, and that distance is 2L, right? So what is dipole? Magnetic dipole is a system that consists of two poles, and that two poles, they are having equal strength, but they are unlike, means they are opposite in nature, and they are separated by a very small distance. So that system is your magnetic dipole. That system is your magnetic dipole. Okay, children? So what is the condition for magnetic dipole? Magnetic dipole, first condition is that the two poles should have equal magnitude. Its strength should be equal. Second, they should be unlike poles, means they should be of opposite nature. And third, the separation between the two should be very small. These are the three conditions for a magnetic dipole to exist, right? Now, here children, the distance between the two poles, we are representing it by 2L. The distance is represented by 2L, right? And this is known as the magnetic length, which is a vector quantity. And its direction is from south to north. So, south to north is the direction for magnetic length. That is vector 2L. Right? Now let's talk about magnetic dipole moment. Magnetic dipole, we understood it is a system which consists of two poles of equal strength and they are of opposite nature. They are unlike, right? And they are separated by a small distance. That is magnetic dipole. Okay, agar magnetic dipole hai, then it will have magnetic dipole moment. So what is magnetic dipole moment? So children, magnetic dipole moment is a term that is used to represent the strength of magnetic dipole to produce magnetic field. So कोई भी magnetic dipole magnetic field produce करेगा तो उसकी strength क्या है? What is its power? That is represented by magnetic dipole moment. Right? Magnetic dipole moment shows the strength of magnetic dipole to produce magnetic field. Here we know that the strength of both the magnets, both the poles, north pole and south pole is same. The strength we are indicating it with small m. As you can see, the strength of north pole is m, small m, and the strength of south pole is also m, right? And the distance between them we know it's magnetic length, that is vector 2L. Okay, so magnetic dipole moment is defined as the product of, so it is the multiplication of two variables. First is magnetic strength, that is m, into the distance between the two poles, and that is the magnetic length, that is vector 2L. Now, this is a magnetic dipole moment is a vector quantity and its direction is same as the direction of magnetic length. That is from south pole towards north pole. Right, beta? Now, this magnetic pole strength, it depends upon magnetic pole strength, that is your M, है ना बेटा? M depends upon the nature of the material, means किससे आपका बार मैग्नेट बना है? सॉफ्ट आयरन से बना है, स्टील से बना है, कोबाल्ट से बना है, निकल से बना है. So it will depend upon that, right? Secondly, it will depend upon the cross section area of the material. It will depend upon the cross section area of the material, and here the magnetic pole strength is directly proportional to the cross sectional area. More is the cross sectional area, more will be the magnetic pole strength. Less is the cross sectional area, less is the magnetic pole strength. Now let's talk about the SI unit for magnetic pole strength, that is M. So the unit of pole strength is ampere into meter, and the unit of magnetic dipole moment, that is capital M, is joule per Tesla, and that is ampere meter square, right? M, we know M, it is ampere meter, and your capital M is nothing but it is multiplication of M into 2L. So your M is ampere meter, length is also meter, so it is ampere meter square. Right, children? This is the SI unit of magnetic dipole moment. Now let's study two special cases. First case, what we are doing is we are cutting the magnet along the length. So like this we are cutting, let me make another straight line. Yes, like this we are cutting the magnet. So when we are cutting the magnet like this, the distance between the two poles, 2L, it is not changing, right? But area is becoming half. Area आधा हो गया ना बेटा, दो पार्ट्स में डिवाइड कर दिया, आधा एरिया ऊपर चला गया, a/2 ऊपर चला गया, a/2 नीचे रह गया. And we know that the magnetic pole strength, small m, it is proportional to area. So as the area has become half, the magnetic pole strength has become half, right? So your new magnetic dipole moment will be m/2 into 2L. So it has become half as you have cut the bar magnet along the length into two equal halves. Now let's see if we cut them vertically. This was horizontally we had cut. Now let's cut them vertically from the middle, somewhat like this. Like this, right? So you will have two pieces. And again, both the pieces will have their separate north pole and south pole. This we know. So when you are cutting it from vertically from between into two equal pieces, the distance between the two poles, that will become half, na beta. It will become, if it was 2L, it will become L and L. So as the length has become half, our M, which was the multiplication of M into 2L, as this has become half, this has become half, the magnetic dipole moment will also become half. Okay, children. So with this, we'll end our class, and tomorrow we will continue further.